So you skateboard to office these days, to work.
Yeah.
Nice.
Maybe orientation is
It's the fastest way.
Yeah?
It's also the cheapest way too, because they're charging ridiculous amounts of money for
You lost a lot of weight.
the working out.
Amazing. Yeah. See,
There's something going on here. Do you want to check?
Something is what? ये है ना दो लोग join किए हुए हैं है ना
Looks like. Yeah. I just thought the volume thing is gonna be okay.
Can you hear me?
How would I know? Somebody.
Maybe not someone-
Yes, I'll have to check. Can you guys hear? See?
Can you change the diet as well? Or it's just
No,
what you
not
do?
really.
Okay. Because
I
being
mean,
in
I
that
have,
Okay.
but I go on and off with being compliant with it. I try to cut out the carbs as much as possible.
Oh, that's where we started.
Last 4 days. Let's see.
It helps. It really does.
Yeah.
Yeah, but you know, it's like the it's kind of an addiction almost. Like you crave it the more you have it.
Yeah.
And so, like, you know, start allowing yourself some more bread and donuts or whatever it is that you like, and then you start craving that more and more. So you have to like be really disciplined, especially the first couple of weeks, and then you stop craving it as much.
Yeah.
But
I
I've
don't
been
have that
bad.
much
I'm
of a
bad.
sweet tooth, but she has like a
Oh,
very big sweet
I am addicted.
Yeah, especially at night.
Yeah, that's
Before
the
bed,
worst
that's
time.
when it's
Yes.
like my willpower is. I'm just looking through the cabinets, like, what can I eat?
Vaibhav, we need to quickly do this. We need to rotate the screen. I don't know. See, this is what we are getting. I don't know what's up. Now, can I just go on it and see what's going on?
Orientation is locked. Rotate device back.
But we already now. Yeah. See now it's. एक बार ऐसे करके.
Is it just like this?
No, can I just see it?
Yeah.
This is perfect, I guess.
Perfect.
Oops. There's something wrong. Can you help me quickly? It goes back to. See, तू टेढ़ा है. तू टेढ़ा देख.
I see. I don't know what to do. What is this?
No, that's just changing camera. Can you just change from here to here?
This one can be like this.
No, how can you open this so that मैं इसको यूँ कर दूँ? Got it? Yeah.
Software clones are segments of code that are similar according to some definition of similarity. This similarity could be syntactic or semantic. That is whether they look similar or whether they also perform similar actions. In literature, there are 4 categories in which clones have been categorized. These are, one of them is type 1. This is identical code fragments except for differences in white space, layouts, and comments. In these 2 code snippets, they are exactly the same. It's just that I've added some comments and all the differences are highlighted with those yellow colors. So that's the only difference in type 1. In type 2, these are identical code fragments except for differences in identifier names and literal values, as well as all the differences that we saw in type 1 clones. So you see that there's I has been changed to N, and some type has been changed to other type. That's it. Then we move to some more complex clones, which are type 3. Here, In addition to type 1 and type 2 changes, you also add, modify, and remove some statements. For example, in this, we see that there's int I here, but there's no int I statement there. That uses for loop, this uses while loop. So these are some additional changes. And then we move on to the toughest category, which is type 4. These are semantically similar code snippets. Both are trying to do the exactly same thing. This uses iteration, that uses recursion. So these are very hard to catch. These are type 4 semantic rules. Now, between type 3 and type 4, we observe that there lies a spectrum of clone pairs. Here, the syntactic similarity between the pairs, it starts decreasing as we move from early categories of type 3 to type 4 categories. And in literature, these categories have been categorized into 4 parts, which is BST3, that is very similar type 3. Second is ST3, similar type 3. Then MT3, moderately similar type 3. And WT3, which is weakly similar type 3, and then merges with type 4. So these are the definitions of type BST3, ST3, MT3, and WT3. Now, I think we are in a place where we can understand what a twilight zone is. So the zone between moderately type 3 and onwards types is that is till type 4 is called twilight zone. So basically, in this part, this is twilight zone, starting from MT3 going to WT3, and then going beyond to type 4 also. So this is a twilight zone, and these are some examples I will show you, like how when we move from BSC3 to type 4, how the complexity in identifying flows changes, and how the similarity increases. So this is an example of BSC3. The highlighted part shows how much differences are there. As we move from to MT3, the differences increase a lot, and then when we go to WT3, the differences increase again by much. And then in the end we have type 4. I haven't highlighted anything here because there's almost no similarity in these statements, code fragments. Okay, so now we are at the position for us to understand what my thesis statement is. It is, I present Oreo, a clone detection tool designed using software metrics, which improves and the most scalable technique known so far to detect clones in the twilight zone. So my focus is to find effectively and in a more scalable manner the clones which are in the in a twilight zone without impacting the precision in earlier categories also. Okay. So what are the problems that we face usually in this zone? To illustrate that, this is a table where I've used 4 state-of-the-art clone detectors, and I've presented some numbers. These numbers are the recall numbers, which are calculated on a popular benchmark called Big Clone Bench. So T1 here is type 1, T2 is type 2, and then the others I just described. So as we move from type 1 till to the right hand side, which is till WT3, we see that the recall of these clones goes down significantly. And especially if we see the twilight zone, there's hardly any performance there. Like Sources CC finds just 5% of MT3 clone pairs, whereas Descartes finds just 12% there in MT3. So we see that there's a decline in the performance when clone detection is carried out in the twilight zone with state-of-the-art tools. Okay, so this is the composition of like manually tagged pairs which are present in a big clone bench dataset. We see that the amount of clone pairs, tagged clone pairs in this data set in the twilight zone, it's huge in comparison to all other types. Now why is it hard? Why is it hard to find clones in the twilight zone? Because clone detection itself is a OS² problem. In order to find clones in large data sets, you have to compare one fragment with every other fragment, which is an N² problem, and it slows down the entire thing. So what state-of-the-art tools do to scale to large data sets is they use some aggressive heuristics, and these heuristics usually cut down the candidates in the twilight zone. And that's why the performance we just saw that is not as good as it is in other categories. And also the third one is in Twilight Zone, that it is computationally more challenging to identify whether two snippets are clones or not. You need to do more comparisons here in compared to other places. Okay. To understand this, I've taken this slide from Hitesh's topic proposal. Here we have scalability on the y-axis and difficulty of doing clone detection on the right, on the x-axis. We see that when we do type 1 clone detection, it's highly scalable, it's very fast, and usually the techniques used there are text-based, token-based, and hash-based. As we move to type 2, our scalability slightly reduces. We use a lot of techniques which are hybrid of text and tokens, and software metrics are also used. Type 3 and then type 4. As we move on the right to the right, we see that the scalability decreases considerably, like significantly. So to summarize, detecting clones in the Twilight Zone is hard. Current state-of-the-art tools do not perform well in this zone, and I want to push the boundary of scalable clone detection into this zone. Okay, so let's move on to what my approach is. This is an overview of my approach. In this, given two candidate methods, I first check whether they are semantically similar. If they are not semantically similar, I reject them then and there. If they are semantically similar, I move forward with them and I see whether they are structurally similar, whether the structure of these methods are same. I do that using software metrics, and if they're not structurally similar, I reject them. But if they are similar, then I say, okay, because they're semantically and structurally similar, I have more confidence to say that I found a clone pair. So this is an overall overview of my approach. I use some heuristics to achieve high scalability and less false positive rates. And my first heuristic is a size similarity filter. In this, I say that two methods with considerably different sizes are very unlikely to be clone pairs. So it's hard for me to say that if a method has like 10 number of statements and another method has 1,000 number of statements, that they're likely going to be close. Probably there's a high chance that they're implementing different functionalities. So this is my first heuristic. This heuristic can lead to some false narratives, especially in the cases of type 4 clones. Just like we saw in the example that the iteration versus recursive example, the recursive example was done in like 2 lines, but the iteration had like 8 lines. Still there was a considerable difference, but in other categories, we haven't observed that much false narratives. Yes.
Is the granularity of clone detection at the method level?
Yes. So I should have said that earlier. Yeah. So I'm detecting clones at the method level, and this tool I've designed so far, I've only implemented this for Java methods. Okay. Using this heuristic, what I do is I take my initial data set on which I want to find clones, and I'm able to partition it into like smaller shards, and then I can perform independent clone detection on each of these shards. So this lets me not only do a parallel computations, but also it reduces the number of candidates, because now my one query needs to consider only the candidates present in that shard and not the other one. So I saved a lot of computations there with this heuristic. Heuristic 2 is my action filter. Action filter, the idea behind this is that functionally similar methods, they probably carry out similar actions in order to achieve what they intend to do. For example, in this method wants to encrypt a string as an input, which is a password string, and in order to do this work, it makes calls to get bytes, get instance, update, digest, like these library methods, and it also accesses properties like length here. So I say that all the method calls and field accesses, they became part of my action tokens. And I say that together, these action tokens, they contain a very strong semantic signature inside there. And if I compare two methods with using just only the action tokens, I'm basically comparing their semantic.
So these heuristics, the size and the action, those are components of that first filter, the semantic one?
So size-based filter is my static filter, which is not about the semantics. It's
Right.
it just separates the data set into smaller data sets so that
Got
I can
it, okay,
independent. Yeah. But this one is about the semantic. Yeah. So this is my structural similarity. Now we know that not all pieces of code that do similar actions are functionally similar. However, it is possible to learn by examples a combination of metric weights that can predict whether two pieces of code that do the same actions are clones of each other. Just like how I explained in the overview, like basically I'm trying to match the structural similarity also here, not just a semantic similarity earlier. And with these two, I say increase my confidence of saying these are close. To do this structure similarity comparisons, I use following these software metrics, and these metrics basically they capture the meta information about a method, like how many loops are present in it, what is the cyclomatic complexity of a method, how many variables are defined in it, how many method calls does it make. And overall, I have like some 25 data points about each method, which becomes the feature for my model. Okay. Also, software metrics, they work very well when our goal is to find type 1 and type 2 clones. Just imagine copy a piece of code, and if you compute the software metrics, they will be same for the type 1 clones, even if you change the identifiers, names, it doesn't matter in calculating the meta properties, like how many variables are there. So for type 1 and type 2, they are pretty robust. They have a good potential to detect type 3 clones, because metrics are resilient to changes in identifier and literals. Also, changing the orders of statements, it doesn't change the metric, the overall matrix that much. So they are pretty robust. However, there are some issues in using software metrics, like especially if you want to use it in the twilight zone. Because now the code snippets might look very different, so they might have very different software metrics. Like the gaps between the software metrics might be large, so it's hard to say when to put the thresholds and where to put the thresholds. So, which leads to a configuration exclusion problem. Basically, if you want to say, okay, I want to say if my number of statements are 10% in range of two methods and my number of loops are in 15% of range, that means I'm okay with it saying that they are closed pairs. But how do you do it when there are 25 points of comparison that you have to make, and how do you decide which comparison should have what threshold? So that is a problem there. Third problem is the candidate exclusion problem. Now, what is the candidate exclusion problem? It's the n-square problem. To compare two methods, to find clones in a data set, you have to compare a method with every other method. And when you do that, that means you are calculating metrics for every method, and then you're comparing that with every other method. So you are increasing the computation for a lot. And then there are high false positive rates, because you're only comparing structural similarity between the methods using software metrics. Unless you have a semantic feature in it, it's very hard to compare the meaning of the methods, and hence the number of false positives increase when we only use software metrics for clone detection. Okay, so to tackle all of this, we thought, okay, let's use machine learning model to solve the problem of the configuration exclusion for us, especially. So what happens is I feed a feature vector of two methods to my machine learning model, and my machine learning model is then trained using some examples to know to look at the features and say, okay, now I can say these methods are clones or not. So we tried many machine learning models to do this on our self-curated training data set, and we found that, okay, the precision and recall are very good for almost every method we tried, but the random forest we took because it was faster for us, and it was also giving us better results. Like, they're comparable, but we just picked this one. But later, we had a collaboration with Professor Baldy's group, and they introduced deep learning to us. And we soon realized that basic neural networks, they were outperforming our random forest models. So we decided to, like, okay, let's go ahead with deep neural networks and learn the metric weights using neural networks. This is the architecture of the machine learning model, SAME's architecture of the DNA architecture that we trained. for our purposes, for Oreo, it consists of two identical subnetworks, a comparator network, and a classification unit. So basically, two methods, the features of two methods are fed into from this side. They go into some transformations here, and then the results of these two subnetworks are added in the comparator, and then the comparator does some dimension reduction in it, and then it feeds one output to a classification unit, which is, I think, a logistic regression model, which spits out a number between 0 to 1. And when the number is more than 0.5, we say we have found a clone. So these models are very good to compare objects. For example, if you want to compare fingerprints, these are earlier used in comparing fingerprints also. And they have a very good property that if a method pair M1 and M2 is fed to this model, or M2 and M1 is fed to this model, it doesn't differentiate between them. It considers both of them same, which is a good property of this model and useful for clone detection.
What's the meaning of 0.5? Or what is the meaning of 0 to 1 that comes out of the...
That is the probability that this model assigns, that whether the clone pair, whether the candidate pair that we gave it is going to be a clone or not. So it's a similarity that this assigns based on what examples it has learned so far in the during the training. So it's does it?
So does it mean that the system thinks there's 50% similarity, or is it that the system thinks with a 50% probability they are the same? Like this will have slightly different meanings.
Yeah. So it's basically something like that, and as my y goes from I think it's something like this. As my y goes above 0.5, sorry, x, this is basically 1 and this is 0. So as I'm going ahead of this range, I quickly jump to 1 in this train model. So basically this means that, okay, when I'm jumping to 1, like as soon as I'm above that 0.5 mark, I'm quickly jumping my probability towards 1. This is how this logistic regression model is trained. So basically any number above 0.5 gives us a confidence that, okay, this model is not trying to say that this is going to be a clone.
Is that the property of these kinds of models, or is that just empirically figured out like 0.5 is the right number for your
So because that's a good point. It's not empirical. Examples also, this is what they use. You can make it stricter. You can say, no, I don't want to say that at 0.5 I want to classify. You can say if it's greater than 0.9, only then I want to say that my model predicts a clone pair. Basically, it depends on what the goal is. If you want to be super precise, you will choose higher thresholds. But if you want to also improve your recall and not want to compensate on that, then you take 0.5. And 0.5 is in the middle. So okay. So we compared this model with other neural network models also, and both on the train and validation dataset, and we found that our accuracy of SAMI's DNN, which is shown in red, is more than others. And other models we compared were logistic regression, shallow NN, and plain DNN. In plain DNN, we didn't have this fancy aperture. We just had one set of layer here, and it gives it here, then it feeds to comparator. Nothing fancy. Yeah. So this is ROC plot and AUC values. Basically, a good classifier has a high value of area under the ROC curve, and we see that, okay, here also Siamese DNN has like best area in comparison to others. Okay, so now that we understand all the constituents of Oreo, let me explain what Oreo's pipeline looks like. So now this is our data set of Java source files where we want to find clones. We first feed it to a metric calculator, which calculates metrics and also action tokens, and put them into this file. Now we perform input partitioning based on that size filter I mentioned earlier, which results into this partition of my input. for each of these partitions, now I can carry out clone detection independently. So what I do is, I choose a partition first, I build inverted index of this partition in memory. So basically, you will see that I have a query file and I have 3 candidates file. Why 3? Because I'm just horizontally splitting these candidate files into multiple files, so that for each of these files I can make a in-memory index.
These files are methods.
These files are methods. Basically, software matrix of methods and action tokens of methods.
Okay.
So each line in this file corresponds to a methods matrix and
Okay.
action
So I just
tokens.
wanted, okay.
Yeah. So I create an inverted index using the action tokens of these candidate methods. Then for every query in my query file, I query my inverted index, and it gives me a list of candidates based on action tokens. So I have some threshold set there, like how many action tokens should I match in order to put these results in as a candidate clone pairs, candidates of this query. Once I have a list of candidates of a query, I make a query candidate pair, and then I calculate the metric hash of query and candidate. If they are same, I say either they are going to be type 1 or type 2 clones. I don't want to feed them to neural networks, and then I find my these 2 clones here. If they do not match, if the metric hash is not same, that means there's some changes there, and I want my machine learning model to handle that case for me, which then predicts whether it's going to be a clone or not. Yes.
So the input partitioning that you do,
Yeah.
that's based upon the size thing that you talked about at the beginning. Is it possible for a method's metrics file or whatever to exist in multiple of the shards?
So, good question. What I do is,
You can just say yes or no.
show that. This one. Good question. Yeah. So I choose based on the minimum and maximum allowed sizes in a shard. I choose my queries. So for this shard, my query size will be between 50 tokens to 100 tokens. Now my threshold for similarity is 60%. So my candidates in this shards will be from the range 30 to 167, which is 60% of 30 is 60% of 50 is 30, and 60% of 167 is 100. So basically, I use this threshold to fit in candidates into a shard so that I don't have to query multiple shards for one query. All my candidates.
Right. So pairs aren't ever done twice.
Yes.
But an individual method's
True.
data might exist in multiple shards, right?
Maximum 2.
Good. Okay.
Yeah.
I just okay.
Yeah. Yeah, so we did this. Now let's move on to the evaluation of Oreo. First evaluation is of scalability, and to do this, we use the entire IJA data set, which is a large inter-project Java repository containing some 25,000 open source projects and 250 million lines of code. These are mined from source codes and Google code. This data set is a de facto standard where clone detection community compares their scalability against, and only 2 tools, that is Sorcerer CC and CloneWorks, have been shown to scale this data set. And both of these tools are hybrid of token and index-based strategies. So yeah, no machine learning based technique or has been shown to scale to this data set. Okay, so we fixed some variables, like system variables, that is, we want to find clones which are greater than 10 lines of code in this data set, which is also standard. We limited our memory usage of each of these tools, basically Oreo, Sources, and CloneWorks, to 12 gigabytes, and we limited the disk users of these tools to 100 gigabytes. This is also a standard way to compare the scalability so that we can have a scalability numbers on a workstation, like how much does a system work on a standard workstation. Sorcerer CC and CloneWorks are really fast. They do the entire job in 4 hours or less than 4 hours. CloneWorks just in 1 hour 50 minutes. Oreo takes 26 hours and 46 minutes. But it's important to note that if you remember, Oreo also finds clones in a twilight zone, and they have really aggressive heuristics to filter out candidates in that job. So that's this. And now I want to show how different heuristics are helping me to cut down on the number of candidates that I'm comparing. Here I'm showing action filter and input partitioning only. So basically what I did is in this entire IJ dataset, I randomly chose 1,000 queries, and then I wanted to see, okay, how many candidates I get for these 1,000 queries when I execute them. So first is my baseline, which is a naive approach. I compare these 1,000 to every other method, and I find these many candidates there. When I only have my input partitioning on, the size-based partitioning that we saw, and we set our action filter threshold to 1%. Basically, I did this to minimize the effect of action filter. I still need it for my system to work, so that's why we have it here. We see that our candidates drop by 2 orders of magnitude just by input partitioning. When we turn on only the action filter and turn off the input partitioning, we see that again our candidates drop by a lot. And when we have both of them on, this is a final number of candidates for the 1,000 queries. So we can see like how both of these are helping us in reducing the number of candidates that we need to compare in order to find whether they are close or not. Okay. Now let's. This is an effectiveness evaluation of Oreo. Again, to do this, we use Big Clone Bench, and we basically use another tool called Big Clone Eval, which uses the output of clone predictors and runs it on the Big Clone Bench database to give you recall number against the manually tagged clone pairs which are present in this dataset. Before we go into the recall, I want to show the distribution of clone pairs found by different tools on this dataset. So y-axis is based on 100%. So these are not the numbers of clone pairs; these are like percentages of clone pairs. We see that Oreo, CC Aligner, and Nicard, they have similar distribution. They find some type 1 clones, then some lesser number of type 2 clones, and many numbers of type 3 clones. The picture changes for, like, say, clone works. It runs in 2 modes, conservative mode and aggressive mode. In both of these modes, we find that it finds a lot of type 2 clones. Sourcer CC has like good balance. It finds good type 3, type 2, and somewhat type 3 clones also. These are basically the percentages distribution of clone pairs found by these tools in different areas.
In 100% is not the same for each of these.
No, 100% is not the same for each of them. So I want to focus on only the type 3 part, and this slide is about actual number of pairs found by each tool in type 3. And the various categories here are like the categories of type 3 that I described earlier. Green is weakly type 3, yellow is moderately type 3, red is strongly type 3, and blue is very strongly type 3. Oreo and CC Aligner have like similar kind of distribution here as well. We find somewhat more number of clone pairs in CC Aligner. Sourcer CC has very little WT3s and MT3s. Mostly it is finding between ST3 and VST3 and other tools as well. CC Aligner is the only other tool which is published in XZ this year, and the only other tool which is capable of or designed to find clones in the twilight zone. And that's why I also included CC Aligner in the comparison.
But does it have the same scalability as Oreo?
It doesn't scale that well. It scale to that dataset, IGA dataset.
So this is using a different data set? I missed.
It is the same dataset. No, it is using the Big Clone Bench dataset.
Okay. So it's not the entire.
It's not the entire. It's not the scale dataset. It's the Big Clone Bench dataset, which is only used to compute the recall of different tools. So it's slightly smaller. Not slightly. It's very smaller than the IGA dataset, which is used for scalability experiments.
So you cannot run CC Aligner on the IG.
No, they tried and they said it fails. Even we tried, and we also failed. After.
You tried that.
We tried their tools. So these numbers are generated by us. Like we tried all of their tools. We contacted the authors, all these authors, and we also authors of the papers where other papers have they have done comparison studies of these tools. So we wanted to use the tools at their best configurations. So we did that. And then after doing that, we have the numbers which are almost same to what the numbers they have reported in their papers.
So when you say it fails, is it like it takes a long amount of time, or is it just the
It
tool just
builds-
runs out of memory? or
It
something?
builds a very big index. Basically, it needs some dimensional matrix into the memory,
Mhm.
and as your data increases, the size of the matrix
Exponentially
increases.
goes on.
Yeah, so it cannot keep it inside. We, however, use partitions, and we only load the partitions into our memory. And these are in-memory indexes, so we don't use that big data structure that they use to put into
Do they also use machine learning?
They don't. Their approach, no approach here uses machine learning. There are approaches which use machine learning, but their approaches, they haven't done any scalability evaluations of their approaches. Also, when we read the paper, we understand that they are not designed to scale. They are only designed to see whether they can predict clones or not.
Because you were not able to run any.
Pardon? Yeah, we were not able to run. We contacted them also, the authors of machine learning techniques, and they didn't have the models ready. They said, I can give you the code, you can run the code and train the model and then do it. But we thought, okay, it's too much.
No vaporware. Too much vaporware for our taste.
Yeah. Okay, so this is basically, you see Oreo finds many clone pairs. A lot of them are in WT3 and MT3 zone, the twilight zone. And now I'll show the recall numbers that we find for these tools. So the recall numbers are almost same for earlier categories for most of these tools. The real difference comes in the twilight zone, where we see Oreo finds 30% of MP3 tagged pairs, whereas others are only finding 5, 3, 10, 0.8, and 12. When we go to WT3 category, we are also almost 0. We have like 0.7. It's the number of tagged pairs in WT3 category is too much. So we also don't perform very well there, but still we perform almost at par with Descartes. Not really in the numbers, right, but in the percentage.
So I'm a little confused. How come here Oreo is doing so much better than CC aligner? What was the previous slide showing?
We are doing here also, like we are finding more clones also here. This is Oreo, this is CCL.
But it seems, I mean, you're doing better, of course,
Yeah.
but the magnitude of difference here just seems a lot less than the next slide. Is this also recall?
Oh, so these are all the clone pairs which are identified by these tools,
Mhm.
and we categorize these clone pairs into different categories based on our heuristics.
Right.
Right? And these numbers here, these are based on the manually inspected clone pairs in the dataset. So these are these numbers are basically should be subset of numbers here, because not every pair in the big clone bench dataset is manually tagged.
I see, so this is just a subset?
Yes,
Okay.
these numbers are only based on the manually tagged pairs in the dataset. So we have the information about that. Okay, this pair is a clone pair.
I see.
This pair.
So in the previous slide, there could be a lot of false positives.
There could be a lot of false positives also. We just separated them in different categories just to show how many number of clones in a given category each tool is trying to find.
And how much of the data is manually tagged? Is it
Um,
35,000?
So 35,000 plus 4,000 plus 4,000 plus 15,000 plus 80,000 plus 7 million. So around 7 million, almost 8 million.
Manually tagged? Who's done this?
So do you want to explain how the Bitcoin bench works?
Yes. So what they did is they said, okay, let's design a strategy to manually tag clone pairs. So they said, okay, let's identify some 45 functionalities in which we want to find the clone pairs. And then for each of those functionalities, let's say my functionality is sort, or let's say search, or no.
Encryption.
Pardon?
Encryption.
Encryption, right? So I'm like,
So a lot of
yeah,
encryption pairs.
yeah. So I will. So then they designed this mini search engine where they basically build an inverted index of each of these tokens, and they search with some keywords like encryption or hash or encrypt, something like that. And based on this, they get a lot of results. Now, when they get these result sets, let's say they get 10 methods which do encryption, and they manually see whether this is doing encryption. Yes. Is this doing encryption? Yes. Is do? No. is this? Yes. So let's say 9 out of those 10 are doing encryption. So how many pairs have we found? We found like 9 combinations of pairs.
They do analysis to see if they're actually clones, because maybe they're doing encryption, but they're not really clones in any meaningful way.
Well, there will be clones
In semantic.
in semantic terms. They're doing the same thing.
So if there are two methods that are doing encryption using completely different algorithms, there would still be a type 4
Yes.
clone? There
Yes.
would,
Yeah, with the definition of type 4, that it is not based on the syntactic similarity, but what the functionality of the method is. So based on that, they found like a lot of clone pairs, and then once they found these clone pairs,
Oh,
then
okay. That's why there's like 7 million,
yeah,
800,000.
yeah, it's not like every pair they saw. It's huge manual work otherwise.
And I mean, we're not entirely sure that all of their classifications. It's not
Yes,
completely
and-
correct. But
and-
this is, I mean, this is the best data set that everybody has to measure with one.
Right, right. And usually if you see that in the card here, it finds 780,000 clone pairs in WT3 category. And when we see the precision of the card, it's just 34%. So anybody who tries to find clone pairs in that category usually suffers from precision loss. So these are the precisions, overall precisions. Basically how we got these numbers are from the clone pairs detected by each of these tools. We randomly sampled 400 pairs out of them, and then we showed these pairs to 3 judges who were kept blind from the source of these pairs. Like they didn't know from which clone detector is responsible for this pair. Overall precision, if you see, CC aligner has 71.25% precision, which is also trying to find clones in the twilight zone. Oreo, on the other hand, has like 82.5. Other detectors work very well here, like Sources CC especially, and CloneWorks Conservative. They find around 95 to 98%. They are 98% or 95% precise, which is very good number. These are like excellent numbers. Also considering that they find more of type 1, type 2, and earlier categories of type 3. So it's understandable. What we did is now we wanted to find precision only in the twilight zone. So basically, what we did is these are the precision numbers I showed you in the last slide, and then we repeated the experiments only for the type 3 category. We remove all type 1 and type 2 clone pairs from the reported clone pairs, and we only find precision for type 3. We did the similar exercise for twilight zone, which is MT3 plus WT3, and only MT3 also. We did not find for only WT3 because in the end we wanted to calculate an F1 number, which is a harmonic mean of recall and precision. This is one number which shows, which combines recall and precision in a way to show what is effective performance of a tool, overall performance of a tool basically. So we did calculate WT3 numbers because if you remember, like for most of the tools, W3 percentages are 0, and if we calculate the F1 score, it will become 0. So,
But how come the precision for Sorcerer, CC, and CloneWorks is high for twilight zone?
Because they don't find many.
because they don't find many, whatever they find,
The one that they found
Yes,
is correct.
whatever they find
Yeah.
is correct.
whatever they find, that happens to be the correct one. So
Okay.
that's really good, but they don't find many. So that's why if you look at the F1 score, basically I should go to the next slide. This one is clearer. If you look at the F1 score, Oreo has 41.8 score, and others are pretty low. Everybody is less than 10 except for CC Liner, which is 17.5. We also did some manual inspection of clone pairs. Actually, a lot of them I think we have judged like more than 3,000 pairs now. But I'm showing you some pairs here. This is a classic type 4 example found by Oreo. Left piece of fragment is doing insertion sort. The right one is doing bubble sort. Oreo was able to find it because it found enough semantic and syntactic similarity in it. Of course, it didn't run the code pair to see whether they're actually sorting, but it happens to be that they share enough semantic and syntactic similarities for Oreo to find it as a clone. We also found this one, an example of MT3 or WT3 clone pair. They are also trying to get an extension of file name. Both of them are implemented like very differently. The tokens, face value of the tokens are different in both of them, and still Oreo was able to find it. We found a lot of false positives also, and most of the time the false positives are like this. They shared like two string append. They shared lot of action tokens, and so semantically they happen to have a similar structure also. It's just that in this case, if is defined outside and that if is inside. Probably these are some of the tweaks we need to put in our when we generate our matrix. That where is if? Is it inside? What is the nestedness of this if? So these things probably will help us. Also, we are thinking, because we found a lot of such pairs as false positives, we are thinking we can take advantage of stop words concept from information retrieval. We can put append, especially, and assert, and length, these three things as stop words, like don't use them as action tokens. And we haven't done these experiments, but probably they might help us. We don't know. Okay, so the summary. We used action filters in Oreo. They filters out a lot of clone pairs, we saw that, and they ensure semantic similarity in the selected pairs. We carry out input partitioning. This helps us to break down a bigger problem into smaller parts, and also helps us to build in-memory indexes, which helps us in faster lookups and high speed. We use machine learning. It handles the configuration explosion problem very well, acting much well than humans could, and it ensures that there is a structural similarity matching. And overall, Oreo works really well, and we got this distinguished paper award for Oreo. It also has some cool badges. These badges say that our research and all the artifacts of this research are available. They have been evaluated by third party, and they are functional, and the functionality has been evaluated by third party. So this has been done over the last 6 years. I feel very lucky to be working with this amazing team. We got Best Paper Award for ICSME, where we did this empirical study of where we compared clones and non-clones to understand whether they are different or not. Then Krista led this study on GitHub, where we tried to find how many duplicates are present in the GitHub. We found okay, GitHub has a lot of duplicates, and we should be careful enough when we want to use GitHub as our data set to find any empirical research. We should remove duplicates if that can affect the research. Then in the end, this is Oreo, which you already saw. These are some of the publications, basically, where I was part of. I separated them in two parts. These are for empirical studies that I did. These are the tools and techniques studies where I was involved. The highlighted ones are the ones where we got awards for. And now I want to really thank my advisor. Thank you, Krista, and thank you, Mondigo Group. You have been amazing. I learned a lot from you, and I will always have this gratitude in me that you turned me into a scientist. So I'm really happy for that. Hitesh is not here, but I really thank Hitesh. He mentored me in early stages and gave me collaboration opportunities. I'm very thankful for him. And Social CC will always be close to my heart. We not only designed it, we improved it. We were able to do the GitHub studies because we made it scalable. Earlier it used to take 4 days to scale the IJ dataset. Now it takes 4 hours after the performance improvement we did. Prasad did amazing work there as well. Farima, thank you for bringing sincerity, hard work, and commitment to the table. Working with you has always been a pleasure, and I would love to work with you in the future as well. You are an amazing team person, and I really appreciate that. These are some kids I know from undergrad. They built a very strong support system for me here, and whenever I needed their help, I could always fall back on them. These are amazing people, and thank you all. And I will be joining them in Seattle in this winter, I've accepted an offer from Microsoft, and most of them are from Seattle, in Seattle. I thank my brother. He made himself available even at 2 a.m. when I would have this crazy idea. I just gave him a call and like, I think I've cracked it. I found something. You have to hear this. And he's like, yeah, tell me what is it. He was always there to critique on my ideas and to build on them also. He was not a co-author on any of the papers, but he helped me a lot.
You shouldn't be anything help you technically.
Basically, he listened to a lot of my things and he asked me a lot of good questions. You remember when I was working on software metrics and I was trying to find how can I find clones with this, and he was also aware of that and he asked me some good questions like maybe you can compare the distributions. What do you get when you do this? I'm like, yeah, I did that. So he was always there to help me out. I can't thank enough my mom and my papa for the love and the blessings they have been sending from a million miles away, and for believing in me. They made a lot of sacrifices for me to be here, and I just can't thank enough. Thank you. And in the end, thanks for joining me in this journey, my beautiful wife Sneha. Thanks for listening to my ideas and then asking good questions. Even though she's not from computer science background, but she does ask a lot of good questions. So I really like that. Thanks for making my life so comfortable and happy that once you were in my life, the PhD life became very easy.
I can understand.
Okay, so that's all from my side, and thank you.
All right. Now the hard part, questions.
Yes.
I have actually a simple question. How do you know with Oreo? Like, what is the story behind the name?
Okay.
We
Yeah.
had an
Yeah.
explanation at some point.
So if you, okay, I'll take it to the line. We have a static filter here, which helps us in separating out candidates into different things. We have another static filter we can say here, which compares the hashes of the matrix. And in between, we have this whole huge dynamic thing going on, which is like a cream of Oreo. So we thought like we have cookies and cream. Also, we were eating a lot of Oreos that night when we were working on this. And we thought, I don't know what to give it a name. Like, what name should we give it to? And like, Krista was like, you have to give it some name. I'm like, Oreo. Yeah. And then we found the reason why. So, yeah. So that's a good question. Any more questions?
So I have a question, and thanks for the talk. So I was just wondering, what are some industry applications of the clone detection tools?
That's a good question. So you remember Oracle versus Google, and the whole case where Oracle sued Google for I think some $1 billion because they thought Google copied some of their code into their Android code. So if suppose Google had Oreo or Social CC, they would have found that, oh, this piece of code is very similar to that piece, and we can probably avoid this whole thing by changing this code or not just using this code entirely. So basically, license violation is one application, then code plagiarism is another, like students copy paste a lot of things and they think they can just copy paste, change the variable names and they can avoid and get penalized, or they'll get full marks in the assignment. So that, and then there's refactoring, like there's like sometimes you have like huge code base and you have one customer tied to that code base, let's say in cases of bank, and then you find another customer which is another bank, and you're like, oh, I can use this entire code base, let me just copy paste it and then customize it for this customer. Now I have this huge 2 code bases. Suppose now I have 5 clients, so I have 5 different things all running parallelly. Maybe if I use clone detector after like 10 years, I'll figure out, oh, these all codes are similar. Maybe we can make a processing unit out of it. Just this is a common part, and the customizations can be kept separate. So refactoring is an important part. There are other cases also, like modern cases like code search, code repair. You can use, you can find clones of a code or not completed code, and you find a complete code and then you put it there, or like try to fix it there, you know. So code repair is a thing. You can find bugs. Suppose you're working on a bug, you're fixing a method, and at that time your IDE tells you, hey, you're fixing this method. I find a very similar method at 10 other places. Do you want to fix it there too? So you can. We build a tool for that also, Sourcer CCI. It is published in XC. So there are many important applications of clone detection. Thank you. Good question.
Well, so to follow up on that, like the main strength of Oreo above the competition is this twilight zone. It specifically for that, like
Applications.
yeah, I mean, so like if I'm in litigation and I'm looking to see whether you've copied my code, I'm not sure that twilight zone
No,
clones
yeah,
would
I
be
get you,
in
yeah.
that category.
Yeah, no, definitely. So the use case, what tool to use where is also a good, thought. Like I will not suggest to use Oreo application cases, but I can suggest you to use Oreo in cases where you have an algorithm written and you want to find is the same thing written differently, and is there an effective solution out there, a better algorithm out there doing the same thing. I want to probably replace my bubble salt with some other salt. I haven't found the cases where I found bubble salt and merge salt as clone pairs, but a clone detector, if that can find it, I'll be happy that, oh, it removes my badly written code and I can change it with like some better written code.
So if that were the application that you were specifically trying to support, specifically, rather than generally, and you probably would give other examples, would you have designed a tool in a different way than you have done Oreo? Where you have something you've just implemented and you want to know whether there's other things in your code base that look like that.
I think Oreo, I would say it's a first step towards going into that zone, the twilight zone, because its approach is very different than what others are trying to use. They're trying to use distance-based algorithms and other things, or they're using just machine learning to find clone pairs. But Oreo takes the same problem and says it, okay, it's not just about using machine learning or other things. It's like let's use everything that we have. We have information retrieval, and we can use that to do things faster and find semantically similar pieces of code bases just by that. And we only use machine learning where we are not sure about the structural similarity part. And that is what I would want a tool to do when I'm trying to find a similar code snippet which is doing the similar stuff but is implemented differently. And in this example, in Oreo, if you notice how Oreo and Sourcer CC are different. Sourcer CC compares some tokens of a method with tokens of another method. In Oreo, I'll just focus on the action tokens. Action tokens are more resilient, more robust to change. Like if you copy paste a method, you can change the identifier names, you can change the types probably, but library calls, for that to change, you need to probably change libraries that you are using. So it's more resilient in that sense, and I think it's a good approach to move forward to find clones in the twilight zone. It's not dependent on the face values of the tokens, it's independent of that, it's more robust in general, I would say. And if you want it to work like Sourcer CC, we can tune, there are things where we can do these tunings, like we can set the tuning of that 0.5 to probably higher. We can, in the action filter also, we can change the threshold. Currently the threshold I think is 55 or 60%. We can change it to, let's say, 70% or 80%, and it will be more stricter there. Probably work like other tools. Yeah. So I think it's a good approach if you want to go in, first approach if you want to go into that direction, but it doesn't solve the complete problem.
But it would also seem to me like if this use case that you had just posed, this is a comparison from one method to many rather than all to all. So you're just doing a comparison with, you could do your filtering and try to bring it down, and then you can do that query probably really quickly, much less than, say, the hours that you're doing for doing all pairwise of all methods that exist.
Yeah.
Because you don't care if something's similar in your corpus, if they're similar to each other. For this use case that you said where, oh, I'm developing this algorithm, is it already developed out there somewhere?
Yeah. So, yeah, in
so
that
maybe
case, yeah, it's
much
about
quicker
that particular
query.
method to other methods, yeah, so it's one to many.
Right.
I agree with that, yeah. More questions?
Questions from the audience?
Do you have any feedback from actual use? Like qualitative feedback, like
How to
this
improve?
was helpful in this way, and I was disappointed that it missed these things, or
Yeah.
Uh,
So-
we still don't have users.
that's what I mean.
Oh,
So-
like other people? No,
Yeah.
no.
Although I know for a fact that some people at GitHub are at least trying to use it. I don't know if they actually use it because they were asking very detailed technical questions
Yeah.
about some of the details of the DNN.
Right.
But
And-
the goal eventually is like is that it will be used by people.
Yes. And some researchers from in China, in Japan also, they are in touch with me, like they met me in FSC, and like one of their students, they contacted me over the email, and he wants to use Oreo, probably for his research, but yeah, there's no industrial use case that I have faced, or a person who's using it for industrial purposes I've faced, but yeah. And Krista, like this guy from GitHub who is interested in this.
So that might be a future step for if this research were to continue.
Yeah. Right. I think my first step would also be, one of the first steps would be to work on the precision. Also, like we already saw like what are the cases which are troubling us, why our precision is going down, and probably we can start from here to like see, okay, can we improve improve the precision without affecting the recall? That should be a case. We also have cases where there are a lot of appends in both methods, and one method is trying to append like a string literal, which is big. Another method is trying to append this words, small. Cases, although they are doing the similar stuff, they are appending stuff, but the string literals are so different. It's just not right to say them that these are clones. So probably we can build some metrics to address those cases also, like which looks into also the size of the string literals, or string literals basically. We have treated a string literal as a string literal. We haven't gone into like whether there are more metrics to qualify a string literal. So those cases can also help us.
Thank you.
All right, if there are no more questions, then I'll ask everybody to please move except the committee and turn off the camera.
Oh, yeah.